In this lecture, I'm going to explain how to solve optimization problems using calculus, in particular using what we've learned about how to use the derivative to find the max and min of a function. So I think the easiest way to teach optimization problems is by just demonstrating how to solve a few of them. There's some general steps that we can take, but in general, each of these are going to be slightly different. There will be some things that you need to basically describe mathematically. You'll be given, all of these are like applied problems, so you'll be given some information and you have to be able to write a function or an expression that describes the situation, and then we can begin to apply the calculus. And that's usually the hardest part for most students, is being able to describe the situation mathematically using a function or an expression. So let's just go ahead and get started, and we can kind of look back. The first one, when we're done here, we'll look back and look at some of the general guidelines that you could use when trying to solve one of these types of problems. So let's say we're given information that we have an open top box and we have the surface area, or the amount of material available to create this open top box, is 108 square inches. All right, and so given that you have 108 square inches of material, we want to find the dimensions of this box that maximize the volume. All right, so one general rule is if you can draw a picture of the situation, that usually helps with being able to come up with a formula or a function that describes it. So you don't have to be a great artist, and I'll tell you right now that I'm not. But let's say this is the front of the box. We just need something to work with, something we can look at so we can kind of imagine what's going on. The other thing that about this box is that it has a square base. All right, so let's say that these two are the same height, or the same length. All right, and then this should be kind of parallel to that one, and we have this back here. So as I said, I have no claim to being much of an artist here, but we just need a sketch, right? So if it's a square bottom, then this is, we can call this x and this x. That's the length of, they're the same side because we have a square bottom. And then we'll call the height of our box h. All right, so now that we've put that information in there, how does that relate to the information that's given? All right, well, I know my surface area. All right, well, so surface area, I've got basically the bottom of the box and then the four sides. It's an open top box, so I don't have to worry about any surface area on the top. So hopefully it makes sense. The bottom of the box is x squared, and then each of these sides is x times h. All right, so we've got four of them. 4x h, and we know that that altogether has to be 108 because that's what the surface area is. Now, in terms of the volume is going to be the base times the width, you know, the height, length, and width. All right, so it's just going to be, the volume is going to be x squared times h. All right, so this is what we know. This is what we want to, in this case, maximize. So ultimately, we're going to want to take the derivative here, right, and then find the maximum of this function. The issue is that we have two different variables right now. We have x and h. So what we'd like to do is write volume as a function of h only or of x only. And this, the kind of the constraint they give us, is usually where we're going to be able to substitute for one of these. So you can see here it's probably easiest to isolate h. So we can do that by subtracting x squared from both sides and then dividing both sides by 4x. So that would give us h equals 108. We subtract that x squared. That would leave us with 4xh. And so we would divide by 4x. That gives me h. And I can take that and put it in here for h, so that my volume now is x squared times 108 minus x squared over 4x. And then I can cancel one of these x's with one of those and multiply. I'm just going to leave this 1/4 out front. 1/4, and it's going to be 108x minus x cubed. All right, that's ultimately what I need. I actually have this. I'm going to take the derivative of this because now I have this. This is actually, we can write it as v of x, right? Now the volume is a function of x only. I've gotten rid of that h by substituting an expression for h that's only in x. All right, so v prime of x, I can leave that 1/4 out front, and I can just take the derivative of this, right, because constants come outside the derivative. That leaves me with 108 minus 3x squared. And I want to set that equal to 0, all right, because we're looking for the max and the min. And so in general, we need to find the critical points of this function. So just as we did before, when just trying to find the max and min of a function, we need to find the critical points here. So we set that equal to 0, and this expression will be equal to 0 when, clearly, when 108 minus 3x squared equals 0. Multiplying by 1/4, the only way multiplying by 1/4 equals 0 is if what's in here is 0. So I can bring the 108 over and divide by 3. I get that x squared equals 36, which means that x could be plus or minus 6. So now at this point, we have to think about what values of x make sense here. All right. So first, x has to be positive, right? I mean, it doesn't make any sense for it to not be positive. So we know that x has to be greater than 0. All right. Clearly, if x is 0, we don't have a box. On the other side, if we look at this expression here, if h was 0, then I would have that x squared equals 108. So x would have to be less than the square root of 108, because if x is greater than the square root of 108, then or even equal to it, then h would be 0 or negative, and that doesn't make any sense. So it's important once you determine what the critical points are, we're going to also check the endpoints of our interval. But in this case, we can see that the endpoints don't make any sense, right? X being 0 gives us no box. If x equals the square root of 108, that also gives us no box because h would be 0. We would just have this flat piece. So since x has to be between 0 and the square root of 108, then the negative doesn't make any sense here. So x clearly has to equal 6. All right, so that's 2 of our dimensions. Now we need h, so we need to put our 6 back in here. So h equals 108 minus 36 over 4 times 6, which is 24, and that gives us, I believe it's 3. Right? So the dimensions are 6 by 6 by 3. That will, for this surface area, that will maximize the volume of that box. All right? So again, first we got an expression for in terms of the constraints, and then we got the expression that we wanted to maximize or minimize. Then we had to replace one of those variables so that we could get the expression that we want to maximize or minimize into one variable, just in terms of, in this case, just in terms of x. Because at that point, then we can take the derivative, set it equal to 0, find our critical points, and think about what values of the independent variable make sense. Kind of what are the range of values? What's the domain that makes sense for x? Okay, so that's one example. Let's look at another one. Suppose we want to find the points. So this is our second one. Points or point closest to the point 0, 2. They're closest to this point on the curve y equals 4 minus x squared. So this one's not too hard to draw a picture of because we're just given a function. This is kind of a mathematical situation where, so clearly the roots here are going to be 2 and negative 2. And So y-intercept of 4. So we're just going to have something that looks like this. And then up at 0, 2, this is my point 0, 2. And what I want to find on this function are any points, I want to find a point or points x, y that are closest to. So this distance right here, all right? So we want to minimize the distance from some point x, y to, or we want to find the point x, y that makes this distance smallest to the point 0, 2. So we can use our distance formula. So the distance between 2 points, I mean, it's really just the Pythagorean theorem, right? So the length of this side is, if this is x, it would be x minus 0, right? And then the length of this height right here would be y minus 2. So those are the sides of our triangle, and the Pythagorean theorem says that the length of one leg squared plus the length of the other leg squared equals the hypotenuse. We'll call that our distance squared. All right? So that's just the Pythagorean theorem. Then we would rewrite that our distance is the square root of, well, x minus 0 squared is just x squared plus y minus 2 squared. So if you know the distance formula, you can just use it. I think everybody remembers the Pythagorean theorem, so I think it's easier just to use the Pythagorean theorem because that gives us the distance formula. Okay, so here is our distance, but this is certainly what we want to minimize. That's clear when we say points closest to 0, 2. But we need to get this now into a function of only one variable because we have 2 right now. But notice we have this right here, y equals 4 minus x squared. So we could just put 4 minus x squared in here for y, and then that would give us d as a function of x only. So if I put that in, I have 4 minus x squared minus 2 squared. So that simplifies to what? 2 minus x squared squared. Okay, so we've got x squared plus 2 minus x squared squared. All right? And then if we were to expand that out and simplify everything underneath the radical, which I'm going to skip that step because that's algebra, not calculus, we would end up with x to the 4th minus 3x squared plus 4. Okay, so taking the derivative, we could take the derivative and set it equal to 0, but there's an important little trick here that's worth knowing. If you have something underneath a radical like this, say we want to minimize that distance, clearly if we minimize the expression underneath the radical, then putting the radical on is not going to change that, right? So if we have something underneath a radical like this, it's a whole lot easier just to take the derivative of this and set it equal to 0 than it is the whole thing, because then we'd have to use the chain rule. It would get messy. It's not impossible, but let's be efficient here. Let's not work harder than we have to. So what we want to do is so we're actually not taking the derivative of d. We're taking the derivative of that. So if I take the derivative, I don't know, let's just call it f for lack of a better term. If we say f equals x to the 4th minus 3x squared plus 4, then f prime is 4x cubed minus 6x. We set that equal to 0. Now we can factor out a 2x here. All right, and that leaves us with 2x squared minus 3. We set that equal to 0. So what makes this product equal to 0 is if this equals 0, then certainly the product would be 0, or if this expression is equal to 0. So in either of those cases, the product would be 0. So in this case, we just get that x equals 0. And over here, if we add 3 divided by 2 and then take the square root, we get plus or minus the square root of 3 minus 2. So I have 3 critical points. Now, now this is the point where we ask the question, what points make sense? All right, what's the domain? What's the range of values that make sense for x? Well, here's the issue. Because we're dealing with this quadratic, it goes on, it keeps going on forever here. The domain of any quadratic is all real numbers. All right, any value of x. There's any value. Clearly, you know, we get down here, we get farther and farther away. It's probably going to be something up in here. But any value of x is a possibility here. So there's really no, there's no kind of endpoints to plug in. We can just look at these 3 points. So we go back to the first derivative test to determine. All right, so if we call this f prime, all right, let's put negative square root of 3 over 2, and we'll put on 0, and we'll put on the square root of 3 over 2, and we want to figure out the sign of f prime, which we have right here. So this is what I'm going to use, and I'm just going to plug in some test values. We know it's 0. We know that f prime equals 0 at these points. So let's put in something smaller than negative square root of 3 over 2. For example, like negative 2 would work out here. So if I put in negative 2 here, that's negative. If I put in negative 2 here, I end up with something that's positive, right? Negative 2 squared is 4 times 2 is 8 minus 3, that's 5. So that's positive, that's negative, so we're negative out here. If I put something in between here, let's say negative 1, that's negative, and that is also negative if I put in negative 1, so their product is positive. If I put in positive 1, that's positive and that's negative, so that's their product is negative. And then finally, if I put in something bigger than square root of 3 over 2, like 2, that's positive and that's positive. All right? So in terms of the shape of our graph, clearly here it's decreasing, 0, and increasing. At 0, it's increasing and then decreasing. And at square root of 3 over 2, it's decreasing and increasing. So I have a min, a local min here, a local max here, and a local min here. So these are the 2 points, right? So I have negative square root of 3 over 2. I want to say 2 points, but they're the x values of the 2 points. So what would be our y value? Well, we would put in negative square root of 3 over 2 for x squared. When we square that, well, the negatives turn positive and the square root goes away, so I just end up with 3 halves. So then I have 4 minus 3 halves, which is 2.5, or 5 halves. So that's one of our points. And then by symmetry, if we put in square root of 3 over 2, we get the same thing. So these are the points that are closest to 0, 2, and also lie on the graph of that function. Okay, so again, in this case, this was our constraint, right? The points that satisfied this had to be on here. So there's our constraint. We got an expression that we needed to maximize or minimize. Well, first we got it here. We used our constraint to get it all in terms of one variable. Took the derivative. Well, we took the derivative of what was underneath the radical. So there's a little trick to keep in mind. Take that derivative, set it equal to 0. Think about what range of values of x makes sense. And then in this case, because we ended up with 3 critical points, we used the first derivative test in order to figure out which ones are minimum and which one was a max. Okay, I'm going to just do one more example. All right, in this case we have, well, in this case we're actually given a figure, so I'll go ahead and draw it. So we have 2 poles. All right, this one is 12 feet high, this one is 28 feet high. In order to stay those poles, a wire is tied to the top and then to the ground, and then, so it's one wire that gets staked from the top of this pole down to the ground and also to the top of that pole. All right, and these 2 poles are a total distance of 30 feet apart. And the question is, where should we stake that wire in the ground in order to minimize the amount of wire that's used in this process? All right, so if we start at the left here, since we don't know where this is going to be yet, I've just kind of arbitrarily put it right here. Let's call that x. That's how far from the left pole we would be when we stake this in the ground. This leaves us over here with 30 minus x. All right, and ultimately what we're trying to minimize is, we can call this I don't know, maybe we call this d1 and this d2. These distances are what we want to minimize, the sum of them, right? So what we really want to minimize is d1 plus d2. All right. But we do have, since these poles are vertical, these are right angles, and we have the Pythagorean theorem at our disposal. All right. So these are, again, now we're again using our constraints. The constraints are I have a 12. When I say constraints, things that can't change, things that we kind of just have to go with because they're the givens in the problem. So one is that this pole is 12 feet tall, and the other is that this is 28 feet tall, and that they're 30 feet apart. Those don't change. We're going to use that information, that known information, in order to come up with these expressions. So clearly Pythagorean theorem applies to each of these triangles, so we can get an expression for D1 and D2. So let's say D1, since it's the hypotenuse, D1 squared equals 12 squared plus x squared, so that D1 equals the square root of 144 plus x squared. D2 squared equals 30 minus x squared plus 28 squared. So D2 equals the square root of 30 minus x squared plus 28 squared. Okay, so we want to minimize D1 plus D2, which is this plus this. Now, unfortunately, the strategy before of just minimizing what's underneath the radical won't work here because this isn't all under one radical. These are related to each other, right? Minimizing one makes the other one, if we could make this really short by going straight down, but it makes this one longer. Or if this one went straight down, then this one would be longer. So there's this relationship between the two of them that both have to be taken into account at the same time. We can't just minimize them separately. We can't just take the derivative of that set equal to 0 and that set equal to 0. That won't work here. We need both at the same time. So, I will say at this point, one possibility is to go ahead and graph this. And graphically, you could at least get a good idea of where the minimum might be. I'm going to show you how to do it algebraically as well. There's also a number of points during this process that you could graph if you wanted to kind of bypass the algebra. And the important thing here is that we are able to kind of represent the situation mathematically and then use calculus to solve the problem. So if we take D1 plus D2, and we're going to take the derivative of that, all right? So here, I'm going to kind of just go through this somewhat quickly. The derivative of this, I'm going to use the chain rule. So we can think of this as 144 plus x squared to the 1/2. So it's going to be 1/2 and then 1 over, right? Because we take the 1/2, well, I'll just show you real quick here. 144 plus x squared to the 1/2. If we take the derivative, it's 1/2, and then that whole thing to the negative 1/2 times the derivative of the inside, which is 2x. And this part stays the same. All right, but of course that is 1 over the square root of 144 plus x squared. So now that you see how we did one, I'm just going to go ahead and do the other. If we were to simplify this first and then take the derivative, we would end up with 1/2 1 over the square root of x squared minus 60x plus 1684, and then we have to multiply by the derivative of what's underneath here, and that is 2x minus 60. Running out of room here. Okay, whoops, and I forgot I have to multiply here also by a 2x. All right, so that's the chain rule. I have to multiply by the derivative of the inside. So the derivative inside here is 2x. The derivative of this was 2x minus 60. All right, so if I multiply the 2x times the 1/2, I can simplify this to x over the square root of 144 plus x squared, and then plus, if I take half of 2x plus 60, I'm left with x minus 30 over the square root of x squared minus 60x plus 1684. All right, and I am setting that equal to 0. So what I end up with, once I move this over to the other side, I have x over the square root of 144 plus x squared equals, and that's going to be negative, so I'll switch those. That'll become positive 30, that'll become negative x over the square root of x squared minus 60x plus 1684. And now they're equal. I have this ratio I can cross multiply, so that gives me x times the square root of x squared minus 60x plus 1684 equals 30 minus x times the square root of 144 plus x squared. Now at this point, to get rid of those radicals, I'm going to square both sides. All right, and what that gives me over here is x to the fourth minus 60x cubed plus 1044 x squared minus 8640x plus 129,600. And on the other side, I just end up with, let's see, is that right? No, that's actually this. And so this comes over here. This is a little bit simpler. I just end up with x to the fourth minus 60x cubed plus 1684 x squared. All right. So squaring this gives me this. Squaring this gives me this. I got those backwards. And then if we put everything on one side, we end up with 640. Let's see, 640x squared plus 8640x minus 129,600. We set that equal to 0. We can divide a lot of stuff out, but ultimately now here's another point at which we could graph, right? We could take this thing and we could graph it and find the roots of it. 640x squared minus 8640x minus 129,600. Kind of ugly, but we can graph it. We would find that the roots are 9 and negative 22.5. All right. So, you know, there's even at this point, after you take the derivative, you know, we could take this and set it equal to 0, or at this point we could take the two of these and graph them and try to find the intersection point of these two because we're looking for where they're equal. There's a lot of points at which we could bring technology into play here to help us find, you know, so clearly x has to be between 0 and 30, right? So x equals 9 does, I mean, if x equals 0, this is going straight down. If x equals 30, this is going straight down. Neither of those really makes sense because it, so x equals 9 is ultimately what we're after here. So this would be 9 right here, and then over here we would have 21. That would minimize the amount of wire used. Okay, so those are just 3 examples of how we can use calculus to solve these optimization problems. Optimization basically meaning we want to maximize or minimize some quantity that's subject to some constraint. So, for example, on the first one we had the constraint that our surface area is 108 inches. Here our constraint was that the points had to lie on this graph. Here the constraint, well, we talked about that. These poles, the height of the poles and their distance apart was our constraint. So we used the constraints to come up with some equations, and then, you know, not always. I mean, they're not really cookie cutter problems. You have to kind of see what's going on. And in some cases, like in the first two, we had the expression that we wanted to maximize or minimize was in more than one variable, so we had to get it into a single. Something in terms of a single variable before we would take the derivative. In this case, we didn't. Everything was in terms of x, but we had a little bit more work to do in terms of the algebra involved. And so, getting technology involved in order to help us solve this is also a useful strategy in solving these applied optimization problems.